Okay, so welcome to Digital Fabrication Studio. You're at the Auto Fab Lab right now, as you know. You found the place correctly. And today we are going to talk about 3D modeling and 3D printing, and thus I would like you. Did you install Fusion 360? Yeah, great. There's one more software, so this slicer like Cura for LulzBot that maybe it's not necessary for you to install it now. I'm just gonna go through it quickly because we have copies on the computers. But yeah, I would like to know whether you did to read something, and do you have something to tell? Not yet. Okay. Well, I'm gonna keep asking. So also feel free. So as I told yesterday, you can borrow a book for a day, and then you can bring it back tomorrow. That's fine. Then yeah. So 3D modeling and printing. So there are several 3D printing techniques or technologies. And during this course, I would like you to create things yourselves. Just like, so I can see you better. So I would like you to create things yourselves. Like if in the basics course you could just get credits, or that's the screens. If you could get credits just by going to Thingiverse and downloading something and then printing that, then in this course I would expect that you just use proper modeling techniques. I mean, I'm going to be talking about Fusion 360, but you can use also Blender or Rhino if you're familiar with it. But I would prefer you to learn something new, referring to the things that I told during the first day, that I would like to see that you grow, that you actually learn something. Yeah, so Thingiverse 3D model prints, not cool. Slicers are there to convert the 3D models into machine instructions. So basically, it's the slicers, they are digesting, so to say, 3D models, and then they are chopping them into lines. I'm going to look at that, and then figuring out how each layer would then be drawn or materialized with a specific 3D printer. And yeah, today we will design something and are going to try to print it as well. So these are the most popular 3D printing technologies today. SLA, FDM, SLS, so stereolithography apparatus, FDM, fused deposition modeling, and selective laser sintering. And somehow there's a lot of information about it on the internet as well. So because 3D printing has become sort of a face for digital fabrication in general. So there are so many other interesting technologies like CNC milling and jet cutting, or lathe, like the classical industrial the tool that was driving the industrial revolution basically. But yeah, somehow 3D printing has become very, very popular. And I am going to use some of the internet resources to help me with trying to explain you what is going on and what these are. So let's start with SLA, stereolithography apparatus, and so there's a Wikipedia article about it and YouTube video. So if we click on the so like so. Enter Firefox stereolithography. Yeah, so there's a Wikipedia article, so I'm not gonna read it aloud, but so for reference, so you just know that this is the page where you can look for more information about it. And I think this illustration illustrates it very nicely. Yeah, that there's this liquid resin into the tank, and then there's this thin layer in between the model and the bottom part, or the glass transparent structure of the printer, and then there's a laser going over certain areas of this thin layer, and producing a solid layer for the 3D model to be built physically. Yeah, so that's that. And then for YouTube, yeah, a YouTube movie was Stereolithography. So let's watch that. Let's skip this.
Stereolithography is a rapid prototyping process used to create parts from 3D CAD data in a matter of hours. SLA is a highly accurate additive manufacturing process and may also be referred to as rapid prototyping or 3D printing. Models created with this technology are typically used as concept models for form and fit studies, or as master patterns for molding techniques. The SLA process begins when CAD data is sliced into thin cross-sections or layers, typically about 0.006 of an inch thick. This data is then transferred to an SLA additive manufacturing system containing a vat of UV curable photopolymer. The machine begins to build the part one layer at a time. Each layer is constructed from an ultraviolet laser that is directed by X and Y scanning mirrors. As the laser traces the cross-section on the surface of the resin, the liquid material is hardened on contact. Once a layer is complete, the build platform is indexed down to make room for the next layer. A recoater blade moves across the surface, ensuring that the thin coat of fresh liquid resin is evenly spread over the object. The laser continues to trace and form each layer atop the previous layer, building from the bottom up. The completed part is then carefully removed from the liquid and separated from the platform. A chemical bath removes excess resin, and the part is cured in an ultraviolet oven. Any support structures are removed at this time. With numerous hand sanding and professional paint options available through service providers such as Solid Concepts, stereolithography has become an excellent economic choice for rapid appearance models. A wide variety of industries have embraced SLA, including medical, automotive, entertainment, aerospace, and consumer products.
So this is more, yeah, like the professional grade. So also like a bit of an advertisement for Solid Concepts. But let's take a look at a bit more desktop-y or consumer-oriented SLA 3D printers, which is the Formlabs Form 2, or now the latest one, Form 3. So. Let's check.
The Form 3 and Form 3L are powered by low-force stereolithography. This advanced print process adapts your part's geometry to consistently deliver flawless prints. At the heart of the machine is the Light Processing Unit, or LPU, an enclosed laser system that uses spatial filtering and a parabolic mirror for uniform illumination across the build area. A flexible tank reduces forces while printing for incredible surface finish with fewer supports, while the LPU provides precisely controlled linear illumination for accuracy and repeatability. Another advantage of LFS is that it works at scale. The Form 3L uses 2 staggered LPUs to offer 5 times the print volume. With twice the laser power, now you can print large parts fast. Easily switch between an ever-expanding library of materials with our auto-dispensing resin system. Integrated sensors ensure consistent and reliable performance at every step of the process. Our simple software helps growing teams work more efficiently, so you can move on to the next challenge. The Form 3 and Form 3L, powering breakthroughs every day.
Beautiful, isn't it? So, like currently our Formlabs Form 2 is broken, so we are actually trying to go for one of these ones, so the smaller one. But basically, this should be the kind of the limiting. It's quite expensive still. So even though it's a desktop printer, like the resin is quite expensive and the process is slow. So this is good for like last prototypes. So for whatever you have. So for example, if you are done with your functionality and you want to make it more, solid and nice to touch or grab or carry around, then probably this technology is the way to go. So when you want to really move into the really polished stage of your product. Okay, let's move on. Stereolithography. Next is FDM, or Fused Deposition Modeling. And again, we have a Wikipedia article. And or some refer to it as fused filament fabrication, FFF. And so this is the technology that is used in the most of the 3D printers that you have probably seen. So because it's the cheapest technique and somehow also the fastest. So you can use it for rapid prototyping. So for example, when you want to create your first iteration of your designing process really quickly. So let's say you work on a model for a day, and you want to have a tangible object at the end of the day. So this is the way to go. It's not necessarily the most precise because you always will have a visible layer height, although with special chemicals you can also post-process and reach a really nice surface finish. But still, it's the fastest. So with FDM, you would do the first 10 prototypes until you see that the functionality is right, and then you maybe would move to other technology, to SLA, or maybe you will start to develop a mold, a tool for injection molding or similar. So let's look at the YouTube video, one of thousands of YouTube videos about this.
In a word, it's a game changer.
It can create parts and geometries that you can't do in injection molding.
That's going to create a revolution in the near future, and this technology will be adopted as a major process for manufacturing components.
And so FDM stands for Fused Deposition Modeling.
It's a fancy word for laying down a small bead of plastic.
What's really cool is you can have a real engineering grade thermoplastic. So the same stuff you'd injection mold.
Someone needs an ABS or a polycarbonate or a high temperature Ultim. We can actually print it directly as opposed to casting a part or having injected molded parts done.
You're getting close to the same quality and mechanical properties and aesthetics as you would an injection molded part, but you're getting it in an additive process.
Our software takes a 3D data file and it slices it into layers. Then that creates a tool path that's sent to the machine.
The raw material is produced into filament like fishing line type form. That filament is wrapped around a spool. So that's your cartridge of raw material that's going to be used to build parts. That material then gets fed up through the machine all the way to the head, where it's liquefied and extruded in fine layers. The support material is extruded at the same time, and then layer by layer, the part is growing. When the part is completed then, it's removed from the build platform, and then the support material is removed. We also offer post-finishing operations that can smooth out those layers. So whether it's a hand finishing or cosmetic paint, we still can provide smooth-looking parts.
We developed the technology to fit a full breadth of geometry sets.
We've seen it used anywhere from small prototypes for mock-ups on test fitting parts to really large structural pieces that go on airplanes or UAVs.
We've gone from that, we're just doing real easy concept models, onesie twosies, to now we're doing production runs of 5,000, 10,000 parts that are, it's the actual part coming from the FDM technology.
So with it, we can do things that I have yet to even think of, but that younger generation, they're going to take this FDM process and turn it into something that's going to blow me away someday.
So yeah, so this is also more like a professional grade video with professional grade machines that are probably very expensive. But yeah, Stratasys actually was the company that was holding the initial patent of FDM, and then sometime in the 90s or early 2000s, the patent expired, and that led to the situation that many companies and individuals could actually develop their printers around this technology, and this is how MakerBot became eventually, and all these other printers that we have at the lab, like Ultimaker or LulzBot or and the Prusa i3, so the i3 open source printer and RepRap project. But then, ironically, like Stratasys bought, as a company, bought MakerBot. So basically, they bought back their invention. Okay, patent expired, but then they bought back the first company that actually showed that they are successful in the 3D printer area. So we could look at another printer, like let's say Ultimaker overview. Ultimaker 2 Plus. So yeah, this is the one that we have, but we don't want to see the advertisements really. Yeah, skip ads. Okay, here we go.
The Ultimaker 2 Plus 3D printer provided by Matter Hackers. Thanks a lot, guys. I really appreciate it. I've had this machine for a while, and I've printed some things with it, and I think it's time for me to tell you a little bit more about it. So let's do this. Are you ready? Go. Welcome back. So here's the Ultimaker 2 Plus. I've had this machine for a few months, and I've had the chance to print a few things, and well, it was just time for me to tell you about this machine, but it's been on the market for a little while, and I need to tell you things about it without parroting what other people have to say. I need to add to the conversation. Can I do that? I don't know. Let's find out. First, let's get into the Ultimaker 2 Plus specifications. It features a build area that is 223 by 223 by 205 millimeters, which is 8.8 by 8.8 by 8.1 inches. The bed goes from 50C to 100C, and it's glass, and it'll get there in under 4 minutes. It's a Bowden-style extruder, and at the end of that hot end is a 0.4 millimeter nozzle, but it also comes with a 0.25, 8.6, and a 0.8 millimeter nozzle because it's got an Olsen block. The nozzle itself will go 180 to 260C, and it'll get there in around a minute. It'll also print PLA, ABS, CPE, CPE+, PC, nylon, and TPU. Last but not least are these sweet LED lights in the frame of the Ultimaker. I know that this doesn't improve your print quality, but if you're like me and you like to film time lapses of your prints, these lights are invaluable, and it turns this Ultimaker into a light box. What's great is these LED lights are controllable from the menu screen. So from the menu, you can turn them on and off, on and off, on and off, on and off, on and off. Now that I've introduced you to the Ultimaker and told you the specifications, let's take a look at some of these prints. Hey, look at this. This is the Eiffel Tower printed in Matter Hackers Pro PLA. The Eiffel Tower turned out incredibly well. There's a little bit of droop when the filament was doing an overhang here in the archway, but it's easily cleaned up, and the stringing that I left could be cleaned up with a heat gun. The sides are good, the top is good. This is a good model. Who could forget Chaos Cortex Bob-omb figure? And look at that. The sides of this model are extraordinary. The Ultimaker's 0.4 millimeter nozzle did an amazing job with the sidewalls of this Bob-omb character. It's a slight curve all the way down, and it's nothing but perfection from the bottom to the top. Yes, I know, my eagle, well, its wings have been clipped, and that's because I dropped it, because I'm clumsy. But I can show you this model because the back and the front of the eagle and the sidewalls look great. This is a color fab bronze-stone material, and other than the wings missing, this is a good model. It stuck to the build plate well, and the printer just handled it. It just did a great job with this model. I'm sorry about the wings. Caw. This gun was a collaboration between multiple printers here in my household. This is Tracer's gun from the game Overwatch. And all of the black parts that you see on this gun were printed with Matter Hackers Pro PLA and then joined to the other parts of the gun. And it came out extremely well. ColorFab released a flexible NGen material, and usually flexible materials are hard to print on a Bowden style extruder, but not the NGen flexible. And here's my little maker coin that I had designed in Fusion 360, and it turned out great. Word to the wise though, it sticks like crazy. They recommend build tech, and it stuck to the build tech like you wouldn't believe. I highly suggest you check your settings and you slowly remove it from the build tech. But this is incredible material, and I've got some cool videos coming up about it. But until then, check that out. The last model I wanted to show you is this maker coin, but it's using Angus from Maker's View's three-dimensional lattice infill. This was printed with ColorFab's HT material, and the material itself is a great material. It's got a good translucence. It kind of glows. It kind of shimmers because of the way the material interacts with the light. This material will grab on to your glass build plate. I highly suggest adding down some EVA glue just to guard against it, because when I removed this coin from the build plate, it also took tiny bits of the glass bed with it. And so that's why I flipped my bed upside down. All right, I'm going to tell you a few things that I think stand out about this printer. The first one is the assisted bed leveling system. The bed is leveled manually, and there's no automatic bed calibration on this machine. However, the machine tries to assist you in the way it levels the bed, and it's incredibly easy to level this bed. Even if you have to add a build tack sheet or a Flex 3D plate to the top, there's no issues. You just perform a few simple procedures, and re-leveling the bed is taken care of. It's by far one of the easiest manually leveled beds I've ever used. The menu system on this Ultimaker is up here on front, and there's an iPod-esque click wheel that takes you through the menu system, where you spin the wheel left or right to get through the menu system, and then pushing in on the click wheel activates your selection. I found the menu to be easily navigated. I found it to be sorted well, and I have no problem using it. The Ultimaker 2 Plus includes the addition of the Olsen block on the hot end, and that allows you to interchange nozzles quite easily. It comes with a 0.25, a 0.4, a 0.6, and a 0.8 millimeter nozzle, and those nozzles are interchangeable when the nozzle is heated up, and then you can use a small little socket to take it off and put the new one on. My friends at Micro Swiss also make plated nozzles for the Ultimaker, and if you need to, they can send you a plated nozzle set for your Olsen block on your Ultimaker 2 Plus. They also happen to throw in a 0.5 and a 0.3 millimeter nozzle. That's awfully nice of them. And finally, I kind of wanted to call out the build quality of the Ultimaker 2 Plus. It's built incredibly well, and I can see how this machine specifically would be really good for high-use environments like makerspaces or educational facilities. If you're going to have a lot of people using this without the availability of downtime, this is built for it. All right, I told you some good things that stood out. What about the bad things? Well, honestly, there's nothing really that stands out about this machine. I guess I could call out the Bowden tube and the extruder setup. In order to insert filament, you're supposed to insert it through the back where the geared motor is, and then you wait for it to appear in the Bowden tube, and then you hit a button and it fast forwards that filament, jamming it into the hot. If for some reason it gets a little too far into that Bowden tube and you advance it using the button, then it's going to jam the filament into the hot end and keep driving, grinding away at the filament, creating a space, and then you have to pull it out, snip off that bit, and try again. Even though I point that out, I did that literally once, and it was the first time I loaded filament. Then I learned from my mistake, and I haven't done it since. And so I can't really call that out as too much of a negative. In the end, this is a very well-built 3D printer that produces incredibly high-quality prints. The assisted bed leveling is extremely easy to use and allows you to add different build surfaces if you need them. And the Olsen block with the interchangeable nozzles allows you to add a nozzle if you want finer detail or if you want to push more plastic through it faster. If you think the Ultimaker 2 Plus is the right printer for you, I put some links down in the description.
Thank you. So that's enough with Ultimaker. We have one of those, and then there's some also in the Vada 3D printing lab. So yeah, they are good. No comments about that. Okay, so next technology that we are going to look at is selective laser sintering. And again, yeah, so there are lots of other materials about it that can explain it probably better than me. Wait a minute, on this one, yeah. So here, so also I forgot to mention additive manufacturing, so which is basically a manufacturing way where you add material instead of removing. So if we're talking about laser cutting, then that's more like a subtractive, and CNC milling is also subtractive, and yeah, like 3D printing is additive. And again, it uses laser, but instead of this liquid resin, it uses powder that it sinters. Basically, it melts the powder and thus creating a layer of the object. Yeah. And yeah, let's look at another video about that.
Introducing Oreo toothpaste.
Great. No, not this, no.
I'm going to talk about why SLS 3D printing may just be the future of 3D printing technologies, but I'm also going to crush a few hopes and dreams in the process. Let's get started. How's it going, guys? Angus from Makers News. So as most of you will know, with 3D printing, it's more of an umbrella term for a huge range of different technologies. Most people are familiar with FDM, or Fused Deposition Modeling, which is the technology that most cheap or low-end desktop 3D printers utilize. But there are other technologies that are now becoming popular in the desktop 3D printing space, such as DLP and SLA, which are liquid resin-based technologies. But what about SLS? Well, SLS stands for Selective Laser Sintering and is a powder-based 3D printing process. It's been around for quite some time, like most of the other 3D printing processes, but the key is in 2014 when a whole suite of core patents for SLS ran out, allowing other companies to start making the technology and therefore dropping the price. So in this video, I want to talk about two such companies, Formlabs and Sintering. And I've got a whole nice box of goodies here, full of stuff that they've sent me, as well as some examples of more higher-end commercial SLS systems. I want to talk about the quality, what you can expect out of these machines, and also what you might need to know if you want to end up owning one. So let's get into it. These are example models from Sintering, a company based in Poland, and Sintering is a desktop SLS machine. They sent me this incredible cube. They sent this insane part-in-part wheel assembly. But what are the advantages of SLS 3D printing? Well, it has a few key advantages over regular desktop FDM, one of which being you don't need support material. Being a powder system, the powder that isn't sintered, selective laser sintering, actually acts as a support for the part as it's formed in the build chamber from the bottom to the top. The platform actually starts here and drops down. You end up with a whole chamber of powder with sintered parts inside. This also means you can have many parts in the same build using a technique called 3D nesting or 3D patterning, whoever you talk to. Because you can have heaps of different parts in the same chamber, in the same build, they're not touching, they have no support material. You simply remove them at the end, dust off the loose powder you didn't sinter, and you have the final parts. There's no post-processing needed. However, you can do things to improve the part finish, and one such thing is sandblasting. So the Sintering team with the Sintering Lisa did sandblast these parts, which has given them a nicer sort of finish over what you'd get raw off the actual machine. Another company that's pushing an affordable SLS machine is Formlabs with the Fuse 1, which is not currently available yet, but you can pre-order it if you want to. And I reached out to Formlabs and asked if they could print a demo file for me, and they were kind enough to do that. So I got this little rabbit printed on the Formlabs Fuse 1. It's just a standard Stanford bunny. I've hollowed it out and done a lattice infill inside it. So in this video, I want to go through and compare both the Formlabs Form 1 and the Sintering Lisa, as well as compare it to some commercial SLS prints like I have here, which I received through Shapeways. These would have no doubt been printed on an EOS system. The original company produced SLS technology, and an EOS SLS system costs well in excess of a few $100,000. So I'm going to compare the quality here, and I'm going to go through some advantages and disadvantages of the different technologies. Firstly, let's start with some numbers. Everyone cares how much things cost. So the Sintering is priced at $6,990 US, and the Fuse 1 is priced at $9,990. There is a bit of a price jump there. That is the raw machine. To get anything else, such as the finishing stations, it will increase the cost. Now, the machines do have differing build volumes. You have the Sintering with a 150 by 200 by 150 millimeter build volume, and a Fuse 1 with a 165 by 165 by 320 millimeter build volume. It's important to note that with SLS technology, you don't have to go that full height with powder. You can just go to the height of your part, but you must go to the extent of the X and Y. You can't just do a bit here. You have to do that whole X and Y up to a certain height that you have set for Z. And that's important when it comes to your materials cost. Now, materials cost for the Sintering is priced at around 110 euros per kilo, or $270 per 2 kilos of powder on their website, and that may change. And the Fuse 1, the prices aren't released yet, but expect it to be around the same. It's estimated to be about $100 US a kilogram. And what sort of powder, you might be asking, is it? Well, it's actually a nylon powder. So the Sintering system sinters nylon powder together to form your parts. These parts are quite stable at high temperatures, and they're very strong. I know the Formlabs team were producing bicycle foot pedals and using them. One of their team was actually using them on their bicycles. The parts produced by SLS are very tough. They're not going to be as strong as a melted nylon, nowhere close, but it's a sintered nylon, and it is quite tough, as well as being quite resilient to high temperatures than you'd expect out of like a PLA FDM part. Now, I have some of these parts in front of me. Like I said, I have this array of fasteners from a EOS machine printed from Shapeways, and I have like this tube from Sintering. They even put Maker's Muse on it. That's nice. And I have this bunny from Formlabs. So looking at these parts together, I'm not sure of the layer heights that we use, but keep in mind that this cube was sandblasted, so the finish is going to be different to the Formlabs print. But looking at the Formlabs one, it's hard to see if there's any real difference between the two. These two are pretty much identical in quality that I can see, and with the EOS print from Shapeways, it's pretty much flawless, as you'd expect from a multi-$100,000 system. You might be asking yourself, why are the parts different colors? Why are the parts in the lower cost SLS systems black while these ones are white? Well, I haven't been given a definitive answer, but I'm pretty sure it's down to the laser power used. Let me explain how SLS actually works. These machines have to warm up. They warm up the print chamber or the build chamber to pretty much just below the point where the material can be sintered. So this can take upwards of an hour, depending on how large the chamber is. And the laser system, which in the case of the Formlabs system is only 10 watts in power, just tips the powder over the edge. And it's really important to minimize the amount of energy going into that powder because of shrinkage. So let's use that to segue into the disadvantages of SLS technology: shrinkage. So, as someone who's worked on SLS builds before, shrinkage is a major issue with even the most expensive SLS systems. And that's because the nylon powder, after the build is complete, shrinks on itself. And you think, okay, I'm used to shrinkage with ABS printing, fine, I understand. It's not that simple. Shrinkage on SLS systems is non-uniform. You have X and Y shrinkage, and then you have Z shrinkage, and it's a different percentage. So hopefully, depending on the software that is brought out with the Sintering and Fuse 1, it compensates for that, but there'd definitely be a bit of dialing in for that shrinkage. Different parts will shrink different amounts, depending on how thick the walls are, how complex they are, and how long the build takes. Also, how long it takes to cool the parts down is really important. I know with EOS systems, the whole build chamber does warm up, but you need to let it cool down slowly. Think about how you temper materials. You need to let the whole thing cool down slowly and uniformly, sometimes in excess of 24 hours in those bigger build chambers to make sure your parts don't just go prone and completely skew out of shape. Another aspect of SLS printing is this. You can actually dye it. Nylon takes dyes really readily. These are industrially dyed through shapeways. They look fantastic, but you can actually get stuff dyed using RIP dye. And a lot of artists actually take the very nice pure white powder from the EOS system and dye them like with tie-dye to create necklaces and all sorts of things. These lower-cost systems are black, so you can't dye them. Again, I believe they're black because you need to use a less powerful laser source to sinter it at a given temperature, but it doesn't stop the fact that nylon is hygroscopic. It absorbs moisture. It absorbs moisture really quickly. If you've been FDM printing with nylon, you know it absorbs moisture almost instantly. And because you can dye it, it's absorbing moisture. Not only because it's nylon, but also because it's sintered. It's not completely melted. The nylon actually can have stuff wick into it. And to show what kind of effect this can have, this is some nylon that's been rarely touched. And I have this guy. So this is this is called Mr. Clicky, and he's a design I came up with in third year uni, and he's been handled by children and people in workshops all around Australia. And look at the difference in color. That's what nylon becomes. SLS nylon becomes after it's been handled. It absorbs the grease from your fingers, it absorbs dirt. Got a bit of red on the back of his head because it touched something at some point. It gets this nasty kind of yellowy color, and the sunlight especially, UV will start to turn it yellow. So this is pretty much pure off the machine, and this is after being exposed to the elements and people over a period of time. And now we need to move on to the bit that these manufacturers don't want you to know, and that is the percentage of powder you can reuse. You might have thought that the powder in these build chambers that isn't sintered can be reused again and again and again. Unfortunately, that's not the case. Nylon in SLS systems gets damaged every time you run the machine. It's heated up, again, just below the sintering point, and then cools down again. And this makes the powder kind of fluffy, for lack of a better word. If you run a system, an SLS system, with high percentage of reused powder, your parts start to lose definition. They get squishy and soft on the outside because it's got all these loose, larger granules of powder that are kind of sticking together as they've been damaged from previous runs of the machine. So you need to substitute powder you've used with virgin powder. Now, both companies I've talked to recommend about a 50% reuse for a good definition part. If you dig through the manuals, they say you can reuse up to 70% if you're willing to put up with a bit of quality loss. Now, I'm sure you could go higher. I know some companies can substitute up to 80 or even 90% reused powder, but you're really rolling the dice. You're going to get some really fluffy parts, and they're not going to have the definition that this sort of thing has. Remember when I first got my first prints from Shapeways, they were using stupidly high recycle rates, and they were terrible quality. You could dig your fingernail into them, and it would just squish right in. You can guarantee that this part has a very low recycle percentage. In fact, it might actually be pure virgin powder. And that leads me on to the next point. To run these machines, you need to have a pretty much full build chamber. Cool 3D nesting, I mentioned at the start of the video, and that's why SLS systems are fantastic for high volume print bureaus and probably terrible to own at home because you're not going to be able to print one thing. You're going to want to print a lot of them all at once in your build chamber. Like I mentioned, you can stop it at a Z height, but your X and Y needs to be used. So going back to the specs of both machines, you're looking at a 165 by 165, roughly that. X and Y, you're not going to just do one small thing on the form, on the Fuse 1. You're going to want to do, 20 of them, which you can do, no problem at all. But you need to keep that in mind. This technology is not going to be very useful for an individual at home. And let's go to our last point, the post-processing. So as you can imagine, you have all this loose powder and you have to pull these parts out of the loose powder. Yes, it is as messy as you can imagine. In the videos, you can see how they pull it out and dust it off and use an air blower to clean it off, and then they use a sandblaster to make the parts look fantastic. In an industrial circumstance, it's fine. You can deal with that powder environment like where I am here, no chance. It's going to be extremely messy. The powder gets everywhere, and you need to make sure you have breathing safety devices like a mask, because the powder is so fine, you can breathe it in, and breathing in plastic powder probably isn't the best for you. So that's going to do it for this video on SLS technologies in 2017. Both Sintering and Formlab have very promising machines to bring the technologies of SLS down in price by a massive amount, to put it in reach of smaller companies. But as an individual, I really would think twice before ordering a powder-based system. You might not know what you're getting into, and yes, these parts produce fantastic detail. As the Sintering produced my tolerance printing test, and everything moves, even the 0.05. It's actually quite incredible. And just check out this book that Sintering sent. The mineral wall thickness is 0.075 or so millimeters, and it basically is flexible like a piece of paper. But you really need to keep in mind the disadvantages that I've mentioned. So thanks for watching, guys. Hope you found this video on SLS pretty useful. Hit that like and subscribe if you could.
Thank you. Yeah, so this was Maker's Muse. Apparently he has a channel. And his video is from 2017. He is talking about his Formlabs Fuse 1. And I think that they haven't released it yet. So you can reserve it by paying 1,000 euros. But it's not there yet. I think that there was, even if it would be available last year, then the Fab Lab would have one. Actually, it had even like a power socket over there for this printer. But yeah, it would be very expensive to print with it. However, I think on the campus in the Ad Lab there's one or several SLS printers if you ever want to use it. But I think Ad Lab is on the move, so it might be not available. Yeah, however, it's also like the same story as with the SLA, like stereolithography, that you know, you would use something like this when you're really sure how the design is going to look like afterwards, so that you are doing the finishing pass rather. Yeah, and then so there are also some online services where you can order parts, so you do not necessarily need to have a lab, need to use the machine alone. Then there are services like Shapeways, where you can upload a 3D model and choose the technology and material to be printed. Yes, this, by the way, I think this is something, Shapeways, upload a 3D model. Yeah, so you upload the model, you choose your material and finish, and then they print, and then they also send it to you, and probably takes 1 week. And last that I checked, so they offer also some metallic powders, so you can print with titanium or steel or aluminium or gold. And then there's another service that is called iMaterialize, which is sort of the same, but I think they focus more on metallic parts. And yeah, the same flow. You upload your 3D file, select material, and finish, get a price, produce, and then they send it off to you. So I saw the parts in one 3D printing, 3D printing technology exhibition, and they were quite convincing. So if you want to make jewelry, so you want to make a really kind of exclusive, posh-looking present for your friends, so you can use these services in order to produce that. It's also not that expensive. So if you are making small objects, then you can end up paying no more than 20 euros for an object. Yeah. So how? Yeah, this is one option that you could also do for your final project, that you focus on digital modeling, so on 3D modeling, and then one of the final prints you order in iMaterialize or Shapeways, and that's okay. And actually, the course budget could cover it also. Yeah. Going back to the slides, what do we have here? Slicers. Yeah, so a slicer is a software that turns 3D models into machine code. So as you saw in the videos, so there were nice visualizations of how the model is being sliced into layers and then drawn. Yeah, it cuts into slices. And at the lab, so we use 3 types of slicers. So first of those is Cura LulzBot, although the first, so Cura is an open source slicer, which was initially made by Ultimaker. So Ultimaker made it and released it open source, and then other 3D printing companies would download it, edit the code for their own purpose, and would deploy with their own 3D printers, like LulzBot. And Simplify 3D is a commercial slicer that is installed on a few of our computers, and it's you can use that to slice for any other printer, but it's just a bit different. So some people say that it's better. I also think it's better, but so it's just different. It provides you a different set of controls. So it's a bit different interface. And then as for the 3D printers, here at the lab, we have LulzBot TAS 6, and Mini, Ultimaker Extended 2, so it was the one that was in the video as well. Then we have a nice testing opportunity. So one of the startups in this building called Mechtageno Industries, they gave us their printer in order to test and gather feedback. So it's also an FDM printer, and then Formlabs Form 2, which is broken at the time. So this is the LulzBot TAS, so the bigger one. Then this is the Mini that we have. So if you switch to camera 2, then you'll see that yeah, we are going to do our print later on this printer. Then this is the Ultimaker. So Laude just printed this green object, which is a replacement part for the noise cancelling headphones. So they broke last week, and he made new ones, a new frame for it. And then this is the Mechtageno one. So the blue tape on the build plate. So this is it's very strong. So it's all, the frame is all aluminium, and then the build plate doesn't have any electronics. So it's just the blue type, which provides adhesion to the first layer of the material, and thus it's less likely to break. So it's you can kind of rely on it. So you can do repeated prints on it very easily, and the surface finish at the end of the process is very nice also. And then this is the infamous Formlabs Form 2. That's during the transportation, during the move, so the resin got into the system, and so we cannot really figure out what's wrong with it. And then in order to make it real, we need to with the FDM printers, we need to talk about 3D printing filament. And here at the lab, we mostly use PLA because of the ventilation. So if you try to melt other material, then it smells really bad, and it's probably not that healthy. So yeah, there are some rolls of ABS, but we try to print ABS, and it really stinks. It's not good. So nylon is also an option, but then yeah, the same reasons. So you should use PLA, and that's nice for rapid prototyping prints, and it can be considered as a limitation for your design process as well. So you need to design your parts if they are force sensitive, if they are going to be used in some mechanical parts, then you just design in a way so that they are most likely not going to break. Then, yeah, before you use the filament with the 3D printers, don't forget them to measure them. So there are two standard sizes. One is 1.75 millimeters in diameter, and the other one is 2.85 millimeters in diameter. So sometimes it goes up to 3 millimeters. So yeah, but just if you want your print to be precise, so in the slicer software, you will need to enter this number. So yeah, it's a good idea to double check that. And yeah, for SLA printing, there's resin, and yeah, if you go, yeah, in the print lab, there are two SLA printers, actually, two Formlabs printers. So if you want to try those out, then I would recommend to go there, book a time and go. And then, yeah, here, like, there's a library of different resins. So actually, so for example, if you want to do bronze or metal casting, then you could you can design your object printed with the SLA printer. They have this castable wax resin, for example, so the model that you make with this, you could then put into memory sand, and then you could heat up the metal, and you could pour in the metal in the form, and it would eat away the wax. Then tough resin is a nice one, for example, for snap fit parts. So if you want to design small cases for small electronics or small things in general, then you can design really tiny fractions of a millimeter snap fit parts and use them. So it usually comes together with this white or clear resin, so the printers themselves. Yeah, and dental, you can, yeah, if you have, if the dentist suddenly tells you that it is really expensive to repair what is repairable, then you can use this probably to print your teeth or whatever yourself. Yeah, so resin, and then focus today is going to be Fusion 360, so CAD design tool made by Autodesk. So Autodesk, you might think AutoCAD. I'm curious whether in the architecture department they still teach you AutoCAD. Yeah. Yeah. They teach you. So yeah, so it's actually outdated. Yeah. Yeah, because like it's becoming outdated. So so people say that AutoCAD is not supported anymore. Also, this format DXF, even though it's very useful still, it's also outdated. So you should try to switch to more recent software. So Autodesk, I think the main focus for them is like this Fusion 360 right now. But then for more advanced stuff, I think there is SolidWorks. There are several online tools like Onshape. Then there's XDesign. I think they just recently launched their service. So it's more like browser-based CAD modeling software, mainly for collaboration. So you would use the CAD software in a similar way as you use Google Docs, which is kind of cool. But then I think the browser technology and the computers themselves are not that far yet. So it's as far as I have used Onshape, so I feel that I need at least 10 or 5 to 10 times more power for my computer in order to be able to use it properly. So yeah, SolidWorks, I don't know, like in architecture, you probably use something like Vectorworks, right? Then there is, in engineering, they use this tool called, like, for civil engineering. I forgot the name. Oh, doesn't matter at this point. Okay, so but let's take yeah, like 10-minute break, and then let's go with Fusion. So I'll open it up also. So you should be able to get a student license for this. Yeah, this year I'm focusing on Fusion, but next year I'm looking forward to actually explore more a tool that is called FreeCAD. Which is open source CAD software, and apparently lately it has been getting really good. So this year and this time Fusion, which is really good and fast, and then next year FreeCAD. Yeah, it has all this full set of tools, so you can do modeling, you can do simulation, as you see, all kinds of measurements, and even generative design. It really haven't tapped into that yet. Yeah, documents, collaborate, and manufacturing. I think manufacturing is the one of the best parts of Fusion 360, because you can go straight from your design into generating toolpaths for a CNC machine, or exporting like exporting STL, like a mesh for 3D printing. It's relatively easy, but then toolpaths for all kinds of other machines, that's where Fusion really shines. So the interface is rather clear. So there are many features, and the toolpath generation algorithms are really nice. Yeah, however, you can do that with FreeCAD as well, but it's a bit not so intuitive. Yeah, but it's gonna become hopefully more intuitive in the future. Yeah, so but let's take the 10-minute break. Just download it and run it. But Fusion is not for free. Yeah. That's true. Yeah. Well, yeah. So here is my Fusion. All right. So yeah. Basically, you have so when you make your Autodesk Fusion account, then you have all these this project space. So this browser, or like the data panel, and you can make folders for projects, and folders inside projects and new projects. And yeah, I'm just gonna go into maybe lab objects, let's say. So you see there are all kinds of existing parts already, and I'm just gonna start from no title, untitled project, but basically what I want to show you are just some basic techniques. I'll design something really simple, like a gear. And in order to start, so usually you start, the flow starts with making a sketch. So make sure that you are in the modeling workspace. So there are other workspaces that you might want to explore, like sheet metal is interesting. So I use the sheet metal workspace in order to produce the design for the water jet cutter, the one, so the design that I showed the other day. And you can do rendering. It has nice, so if you need to present a concept of a design to someone, you can use that. So you can do animation, simulation, and manufacturing. This is what we are going to explore tomorrow. And you can create all kinds of drawings for sending off to manufacturing houses and so on. So in order to save to start a project, you start with clicking on Create Sketch. You click here. And yeah, it's gonna bring you in a two-dimensional plane where you can see the origin or the crossing point of X and Y axis. And yeah, let's start with circle. And when you can access all kinds of drawing tools under the sketch menu here. So you can start with line, rectangle, circle, arc, like all the tools that you would usually find in CAD software. So I'm going to choose one of those, which is center, diameter, circle. And in order to start the drawing, I need to click once. As you see, there are also labels appearing that guide you through the process. You click once, and then you move your mouse, and it expands. And let's make this first circle 1 centimeter in diameter, or 10 millimeters. So the units are important in this case. There was a place where you can set up the units. So if you go to your account, this account representation button up here, and you choose preferences, then you can access the preferences, and there is default units, and you should select millimeters. It might be that it's inches, but we're in Europe, we should use millimeters. Yeah, and then once the circle is created, you can also drag the dimension around like so. And so the good thing about CAD programs is that this is editable. You don't need to go back with Command Z or Control Z, so you do not need to undo and redo, but you can just edit some features like this. For example, if you want to make it 15 millimeters, then we can just easily do so. Let's leave it to 15, and let's draw another circle. Let's go to the sketch circle, draw center, diameter circle. Let's draw another one, and let's make this this one like a 10 millimeter one. Now I'd like to select the label and pull it out a little bit. Yeah, like so. Now we have 2 circles. The reason why you'll understand later, but yeah, so these are going to be the inner. This is going to be the inner part of our wheel in a way, and imagining that the rod that we are going to use for the rotational part of the wheel is going to be 10 millimeters. So this is going to become empty, and this is going to have a material. Let's draw another one. So go to the sketch, central diameter circle, and draw it. And let's make this 5 centimeters, so. And another one. And let's make this 40. And the nice thing is that yeah, when you draw and you specify the center of the sketch as the center point, then all these circles, they are snapping to it. However, we can delete this little icon here, so we can click on it. So it's a constraint icon. They're layered up like so, and then when you delete those, then you can move these circles around like so. So there are more. These, yeah, they are somehow perpendicular. Oh no, coincident. Yeah. So delete those. And then can I? Yeah. So move them around. So also one nice thing about CAD software is that so it does respect the things that you learned at school in terms of geometry. So you know, when you want to make things parallel to each other, you want to things snap to each other, you want to have a certain angle between parts. So you have all these features here. Like you have all these things: coincident, concentric, and whatnot, tangential. So for example, if you draw a line, then and you select that line, and you can select this tangential constraint and select the circle, and you know, now the line is always going to be tangential, so it's always going to touch the circle in one way or another. Or if you move the circle, then it's just gonna snap to the line like so. But yeah, we are not going to use this feature at the point, maybe in a moment. But yeah, I just wanted to demonstrate the power of constraints by actually manually placing them, so not allowing. So when I started to draw these circles, then it was more like automatic. The first thing that the program did, it applied this coincidence circle to the in between the center of the circle and the center of the stage. It's like so. So whenever you select this coincident constraint, you have to select 2 points after one after another. So I will click on the center here and the center of the circle, and one more time, center of the circle, center of the sketch, and also for the other one. And now we're back. Yeah, so that looks like this. And I hit escape in order to exit the tool. And now we have a sketch, so we could use also as a drawing, so in order to explain somebody what is going on and how big an object should be. And then we hit on stop sketch, and now we are back into 3D view, 3D representation of the model, like so. So we can rotate around. And in order to make a 3D representation of this, we need to use tools that are around this create menu. So there are a lot of options. You can extrude, revolve, sweep, loft, rib, web, yeah, whatever. We are just going to stick to extrude. So this is the most used tool in order to create shapes in the modeling surface, in the modeling workspace. And in order to extrude, so when you select this tool, then you see that the panel appears, and it asks us for a profile, and the profile means this. So this one face of the sketch. So we can select several, but we are going to just start with the outer one. And then there are some settings which you could choose. You can choose like the starting point, so which is by default is the profile plane of the sketch. But you could choose also it to be an object, or you could offset it. Then we can choose the direction. So one side, so as you see, you can extrude it up or down. But in our case, we want to extrude it in symmetrical to 2 sides. Yeah, you can extrude 2 sides, but we want it to be symmetric like this. And we can specify the height of it, and let's stick to 10. Then, yeah, the extent, we can select a distance or all. So if we are cutting through another object, then if we select all, it's just gonna extrude it enough in order to cut through the object. And the distance, so this is the amount we want to have, and also the measurement. Yeah, so now it seems that 10 millimeters, it's in both way 10 millimeters, so it's 20 total. So here we need to use this icon. It's going to be the whole length, so we want it to be 10 millimeters full width like this. So, and we also can specify a taper angle. So we can extrude in an angle. So maybe this is going to be some sort of a gear that is going to fit on a rail. So then this could be useful. So 15 degrees looks kind of fine. That could be interesting. And then we hit OK. And we are left with a 3D object like this. So after extrusion, the sketch that we used is automatically hidden, and then in the browser panel over here, we can actually see all the objects that we have on the stage. So they are separated in categories. So there are bodies, and there are sketches. So these are among the basic ones. You can also hide and unhide the origin. So yeah, and these little light bulbs, they are kind of they are telling you that they're representing visibility of an object or of a specific category. Yeah, there are document settings, for example. So yeah, origin means that these are all the tools that you would need to use in order to orient your model against, and bodies and sketches. And we need to show the sketch once more. Okay, origin, I will hide that as well. And let's do another extrusion. So this time I'm just gonna hit E in order to extrude, or yeah, you can check this, click this icon, select the profile, and also I'm going to do a symmetric extrude. And also I'm gonna focus on the whole length, and this time it's gonna be 6 millimeters or even 5, like so. And in this case I'm not gonna use any taper angle. I'm gonna create a new body and hit OK. And now we see we have 2 bodies over here, like body 1 and body 2. So we can rename those by double clicking. So outer, inner, and the sketch is here also. Yeah, and then so we need something to connect the outer and inner parts of the wheel. In order to do that, we could use the same sketch, or we could create a new one. So since it's just a simple object, then we could create yeah, another cool feature actually is that you can start to sketch on top of existing surface of an object. So let's do that actually. So let's hit on create sketch, and let's create a sketch on this surface over here. And basically what we need is like a shape like this that would connect. But it did somehow weird things. I'll just try to not constrain it. Let's just do it relatively randomly. So yeah, there are some things that Fusion added automatically for me. So for example, this parallel constraint. So when I'm moving these points, then these 2 lines are staying in parallel. So I can also delete these. And then when I move these points, then it's totally unconstrained. It's yeah. And this is still perpendicular to something. Yeah, I'm just gonna delete it like this. Yeah, let's start from scratch. So let's first of all, of course, make these 2 lines parallel to each other. So like so. The 2 other lines we don't need parallel, but we want one of the lines to be parallel to the x-axis. Let me see which one of those would be the best. Collinear. Can I select an axis actually? Let's do this from scratch. No. No. Let's add another line that is going to be kind of a... I wonder what is this specific constraint. I think it's somehow like a ground thing. Okay, let's just make this as a construction line. So it's one point is coincident with the center point of the sketch. but let's make it a construction line by using this construction icon. So it's gonna appear as a dashed one, and then let's make this one parallel to that. So let's click on parallel. Ta-da! So we have it. Then another thing that I would like to do is to create a midline here, which is gonna be also a construction line. Not coincident, but a construction line like this. And we want to make it perpendicular to one of these lines. So let's select the perpendicular. So this is what I'm telling you about the geometry lessons from school. So they are actually useful in this context. And now you see it's kind of, when you drag around the corners, then it's moving in a certain way. It's going to convert this into a construction line as well. Next thing that we want to do, we want to also snap it so that it aligns with the center. So we can use the collinear constraint. So we click on this, and then on the line, I don't know, I'll need maybe to use the coincident one, this and that. Yeah, now it's on the same line. So now what we can do, we can move it up and down like this, but not sideways. So now, yeah, so these are going to be equal, and the side lines, they are going to be symmetrical anyway. So now we need to decide on the width of these. So in order to do that, let's use the dimension tool. So you go to sketch dimension, select these 2 points, and then you can make dimension in between those. So let's make it 5 millimeters here, and let's do the same with the bottom, but instead of 5, let's select 8 here, and yeah, let's move it around like this. And now, so a good idea is actually to constrain the sketch completely. So in order if you change something, everything changes together in the future. So that's kind of a concept hard to explain. But so you don't want to have things like these that you can move it freely around. So that's kind of bad. So it produces unpredictable results. And the way to see whether your sketch is fully constrained is that if you look at the browser here, then you see the first sketch is fully constrained, and you see there's this little pin there, so that means it is fully constrained. And for the sketch 2, it's not the case, so it's still you can move it around. And in order for it to stick, instead of like using precise dimensions, this distance from the center, we can also reference it and snap it to the underlying sketch or underlying object. So we can click this coincident thing on the point, and then here on the line. And now it's going to snap to the inner line. And if we move these points around, so you see that now the only thing that is unconstrained is this bottom line. That means that we could actually snap it to the inside of the outer circle. So let's do that. We're using coincident and the line, like so. And yeah, so theoretically now it should be fully constrained, but it doesn't appear so. Fusion doesn't think that for some reason. I don't know why. Maybe because of this one. It should be maybe a certain length, or I'm gonna snap it to here. Yeah, now it has a pin. Now it's fully constrained. That's okay. Now I can stop the sketch. And yeah, and the sketch is going to appear, you see, on top of the plane over here. So yeah, what I want to do, I want to extrude it so it actually merges together with the inner and outer part. So I will go to extrude, this one here, and I'm extrude downwards like this. And so yeah, the direction one side, but for the extent, this time I'm going to select two objects, and I need to select an object, and the object can be a face. So a face of a 3D object is considered an object. It's gonna extrude to the face over here. And I also can add taper angle, but maybe not in this case. No, it's a bad idea. And you can choose the operation. So previously we saw that it's going to be a new body, and now it's offering the join operation as the default because it's intersecting two objects. So it thinks, do we want to connect? But not right away. So I'm just gonna create a new body at first, like so. The reason why I do that is because I want to use pattern, which could be a circular pattern. So I want to create copies around an axis of the object. And when I click on pattern, a circular pattern menu appears, and I can select bodies because this is the object that I have there. It's a body. And then I need to select an axis it's going to rotate around, and in this case it's the Z-axis. And yeah, here, as you see, it also previews us with these, and we can change the quantity, and it's going to automatically change the appearance. 6 or 5. I'm going to stick with 5. 5 is nice. And okay, so now we have 5 objects. Yeah, I wonder. Yeah, I'm not gonna really extend the complexity of this design anymore. Yeah, and then the next thing is to merge them all together. And you can do so by using modify and combine tool. And it's gonna ask you for specifying the target body, which is gonna be the outer shape of the outer part of the wheel, and then tool bodies, and these are all the other parts that have to be merged together. So we're just gonna select all of them, and yeah, you can choose the operation. Instead of join, you can also use cut or intersect, so you can cut pieces out. So let's see how that actually goes. Yeah, it didn't do anything really. But yeah, if something like this happens, don't worry. You can actually look at the timeline underneath. So another good thing about Fusion is that you can actually roll back in time and operation by operation, and even better, you can actually each of these operations you can open up by double clicking, and you can change them like so. I think we'll need 2 operations over here. So first we'll need to select these guys. They didn't join together. Why? Ah, yeah, because they are not really connected here. So that's a problem. But we can fix that by going back to the sketch. And fix that by going back to the sketch, double clicking on it. And the problem is actually that we snapped this line to the top part of the outer wheel, and it doesn't really intersect with the inside of the body. So we click on this, and we delete the coincidence, and we can move it around, and let's coincide it with the middle part, like so. And now let's check whether it's fully constrained again. It is. We stop the sketch, and yeah, now when we go here, we can again reselect everything, and it should supposedly merge everything together in one object. Still not one object for some reason. cause, probably, of the extrusion. Yeah, we need to select all of these also. So yeah, I didn't extrude the whole object. Okay, and now when we move forward again, now we have one solid object here, so it's all one. Then, yeah, at this point we can do, let's do something with cutting. So for example, let's just, last thing, so I'm just gonna create a little hole somewhere over here, a little circle somewhere randomly. And yeah, you can create a circle without an automatic dimension as well, and you can just add it later. Let's just sketch dimension, and let's make it 2 millimeters big. I'll create a line that I'm going to use as a construction line over here, and place this in the center of the line by using the midpoint constraint, like so. Now it's snapped, and it's also fully constrained, so we can stop the sketch. And let's choose the extrusion tool, select this, and now we can start extruding it downwards. And instead of, you know, going for a random, so we could go full way through like this, but we can also select an option that is all, and it's just gonna go a distance that is just enough to cut through the object that it is intersecting. And we need to select the cut operation and hit OK. And now it has a hole. Yeah, we can use it for whatever. Yeah, and at this point we can actually export it for 3D printing. And in order to do that, here's the Make menu and 3D print. That's fine. So we need to select something. So it's gonna be the one 3D object that we just created. Preview or not preview mesh. These are kind of default settings. They are all right. And yeah, for the output, if you don't have a slicer installed, then uncheck this, and it's actually nicer just to get a STL file as an output and hit OK. And it's gonna ask you where to save. Save it on the desktop, new folder. Wheel STL, say. And at least on Mac OS, it is that that you can actually preview the file in Finder. So here's the Finder. Let's go to desktop, DFS, wheel, like so. And yeah, it's a valid STL file, like so. Yeah, then next step. We need to get a slicer. So where we have our slides also. Next one, slicing and printing. Yeah, so we will slice it and print it. Demo. So we are going to use the Cura LulzBot version. You can download it here. But you don't need to download it now, because it's also installed on the computers over here. But you can, it's just to demonstrate to you that you can actually install it on your computers and do the slicing yourself if you know the parameters. Yeah, I have it here on my computer. I'm going to open it up. here we go. So this is the interface, and so yeah, on the left side you see a representation of the printer. By right-clicking and dragging, you can rotate it around. Middle mouse button is going to move it, pan it around, and then if you use the mouse wheel, it's going to zoom in and out. Let's import the model. So in order to do that, we need to open files. We go to desktop, to demo wheel stl open, and yeah, you see it's imports it in the right size, and yeah, it's quite big. It's gonna take some time to print. So what I would like to do, I could actually scale it to have to be 2 times smaller. And here, if you select the object and you go to the scaling tool, you can do that. So I'm just gonna decrease it by, say, 75%, not 50 really. No, okay, let's do 50. Let's go 50.
But then when you imported it, it came
In the actual size,
yes.
in the actual millimeters. Yeah, if you use a CAD software, you export it, and an STL file actually remembers the units that you use, and it also remembers the numbers, obviously, and then the slicers they pick it up. Yeah, you can rotate. For this we don't need it really. You can move it around if you want it to be on a different place or on the build plate. So you could, you know, like put it in a corner, like so. Maybe because the build plate is less used in the corner or whatever. And then here you select the model of the printer that you have. So we are going to use LulzBot Mini, and yeah, for the material, you can just select PLA. Ultimaker setting is fine. And profile. So, but now it's gonna be somewhere. Now, yeah. Okay, so these are the. So now we can see the settings that we need to set. So 0.1 layer height, that's maybe too not enough. So let's go with 0.2. Initial layer height 0.3 is fine. Line width, so it depends on the nozzle. So we had 0.4 nozzles, so 0.4 is probably fine. Or for the minis we had 0.5. 0.5, okay. So then we go with 0.5. Then shell, top bottom line width. So also I think we need to go with 0.5 over here. So on the actual slicers on our computers, so all these parameters will be basically set for you, but just for the first time I'm gonna check. So wall thickness, yeah, 0.8, 2 is fine. Top layers. So this is kind of fine. Then another important part is the infill. So normally it's 20%, so it's the amount of material that is going to fill the inside, the invisible part of the object. Yeah, so 20 is nice. Then for the material, since we selected PLA, so this is pre-filled, so there's more or less the default settings for heating up PLA plastic. And speed and travel will leave the same. Another important part is support, because as you see, if we zoom in, that it's not perfectly. So you know, it's not. So it's a bit above the ground, above the build plate. So it's probably not going to print well in the air. So you need to add some supports. So let's add those. Generate supports everywhere. Zigzag, and this is probably it. Make overhang printable. Maybe. Okay, now it's slicing, and it's ready to save the file. But then, if you change the solid view to layer view here, then you will actually see how it's going to be printed. And this is a nice way to check whether you haven't forgotten something. And yeah, so you see, you can also see how much time it's going to take to print. Here it's going to be 9 minutes. So actually with 9 minutes we could go for a bigger size of the object. So I was worried that it's going to print too long, but let's go for, instead of 50% to 75%, so it's going to be a bit more detail, like so. And then yeah, now it's sliced. Again, we can go to layer view and we can check how it's going to be printed, and this time it's going to take 23 minutes, which is kind of okay. So because after we set up the print, I would like to switch over to watching Fab Academy. So this is one of the things that I promised to you. So they already started actually, but yeah, let's first set this up. So I'm going to save this to file. I'm going to go to desktop, 3D print demo, LM wheel G code. So yeah, mind the G code extension. So it's kind of an old format for that most of the machines use in order to describe how the axis and how the specific parts of the machine should behave. So I'm going to save, and I'm just to demonstrate to you how does it look in a text file. So it's actually not that magical. It's just oh no, that's the STL file. Sorry. EDF. Wait a minute, where did I save it? 3D print demo. Ah, okay. I wanted to save it in the digital fabrication. Yeah, here. That's why. And yeah, this G code file open. So this is how it looks like. So first there are some comments, some meta information about that, and then yeah, this comes even together with some explanations of what's going on. So this M73 E0, these are special instructions to the actual board that LulzBot uses. Disable fans, matrix, absolute positioning. So set extruder to position 0. Start heating up the bed. This is probably the temperature. No, M is 140. That's like temperature, and then home O axis. Retract filament. Wait for extruder, and then these are the position already. So it's for wiping. So it's gonna trying to clean the nozzle. So it has an integrated function for that. And yeah, and this is the part where it actually starts printing. So it specifies x and y coordinates, and then how and the absolute value for the extruder. So it's no absolute, but actually relative value. So how much of the filament should be extruded. So it says, I think it's 1 millimeter, 1.32, and the rest. Yeah, that's it. And here at the Fab Lab for the LulzBot Minis, we have everything available online. So if you go to, it's also available only at the lab. So if you go to fablab.alto.fi/3D printers, then here are the LulzBot Minis, and we'll do something with a mini number 4. And in order to do something, we actually need to log in. I just need to remember what was the password? I think I had it. Oh. gonna save it. Yeah, once you are logged in, then you see so it's basically a Raspberry Pi that is connected to the LulzBot printer, and it's kind of a proxy or in between us and the printer, because the mini ones, they don't have user interface built in. So, and then the Raspberry Pi is connected to the printer via USB port, and it's using serial communication. So, and you just need to hit connect in order to connect to the printer. So the Raspberry Pi connects to the printer, and once it's connected, you can see all parameters related to it in this part, on the right part of the window. And you can even control it. You can move the X and Y axis and things like those. You can hit this home button, and I think you cannot do anything right now because it's actually turned off. So I'm gonna turn it on. You can actually come with me. So for the ones who are watching the YouTube channel, then you can just switch to camera 2. Like here, hello. And here you see there's the on-off button over here. So you just need to switch it on. Yeah, and now it's on. Now we have to go back. Well, we are gonna come back here one more time. Yeah, and at this point, so we need to hit connect again because it was off. So if it's off, normally it cannot communicate with the Raspberry Pi. So we need to hit connect. Now it's connected, and now we see that you know, these parameters become available. So luckily we don't have to load the filament today, but I am going to show that individually to each of you when you are going to print something. But what we need to do, so here's a list of jobs or G-code files that have been printed with the printer. And what do we need to do? We just need to upload ours. And yeah, make sure you don't upload the STL file. It's not going to do anything, but we need the G-code file. So we hit open. And all we have to do is to hit load and print here. And this is the point where, yeah, where it starts to do things according to the G-code. So here we can see that, yeah, the bed temperature is starting to rise. And also the nozzle temperature is starting to rise. So these colors, so the blue color stands for the bed temperature, and the red color stands for the nozzle temperature. Yeah, and now we can just move. Now we can go to the 3D printing room and we can see how it works. And again, a reminder that there's the second camera. So also, if you're gonna watch the recording, then you at this point you can switch to camera 2 and see here. It's gonna take some time for the bed to heat up, so for 1 or 2 minutes. Ah, yeah, now it's there. And you see there's this pad here. It's gonna use that for wiping.
You can use only one material.
Yeah, these have, so this is like a single extruder, but there are also printers with multiple extruders, which are able to print the support material or different colors at the same time. But yeah, here all of the printers that we have are single nozzles, and we generally use PLA. So for rapid prototyping, it's just enough, unless there's a project that is really good for us and you know, rather experimental, then we can try to experiment with different filaments. But in most of the cases, like 95% of the cases, PLA is just fine.
then the wall and the infill, since they were just why are they different?
So if there's more, the more infill there is, the more shrinkage. So it's kind of tends to shrink more, and it eats up more material. So also, if you're printing outside of the course, then it's 7 cents per gram. So which means if you end up with 50 grams, then you multiply that, and it goes like that. And generally, there's enough plastic in the world, so you should try to reduce the amount of trash plastic by reducing the infill of your 3D print. So now it's did the cleaning of the nozzle, and it's heating up the nozzle for printing. Let's see how it goes. I hope that I set the settings right.
So the infill now could have been less denser than what being kept in the model.
Yeah, I mean it's 20%. That means that 20% of the space inside it's gonna be filled with material.
Okay.
So the normal number is 20%, or
Usually it's 20. Yeah, unless you need something specific. If you want to be heavier or more rigid. Yeah. And it's usually a good idea to watch it for some time so that the first layer gets printed nicely.
Isn't there like these materials like corn cables made from corn?
I don't know what it could be. I need to do a bit more research about that.
Because last year, one of my colleagues made this laminating tablets with the corn cables.
Yeah. Well, we have some. So usually it's a mix of PLA and something.
Okay, it's
But maybe that was.
pure.
But it could be that it's actually the PLAs from corn. I need to read on a little bit more. But there are some different filaments. For example, there can be PLA mixed with wood particles, for example. So it at the end of the day it creates more of a wood-like appearance. Then there are translucent. There are even flexible versions of PLA filaments, so like Willow Flex or Ninja Flex. So you can do like shoes inlays for shoes or all kinds of flexible stuff. So yeah, now we wait for 20 minutes, and meanwhile it's printing. We can switch to the Fab Academy. So in order to do that, let's open Zoom application. And I'm probably going to stop streaming from this screen now. No, I'm not. Not yet. Okay, so it's still, it's actually still a preparation phase. Yeah, so they're actually going to start at 4. So it's the 3:30. It's going to be preparation, and then yeah, which is nice. So we can now have a small break, and maybe if you want, you can create something simple for you to 3D print, and we can set it up on one or more printers here. So you just get the idea better. Hey. So looks like it did it.
The brush, or maybe start?
Yeah, the brush. No, I think the brush, because I'm gonna clean the machine later after. I think with the air. Yeah. So there's a container on the bottom.
There. What?
Like there's kind of a container here which collects all the dust.
Ah, okay. So if it's pass on these.
Yeah, yeah.
Maybe should still use the vacuum.
Can I?
Or maybe this.
Looks alright.
Yeah.
There are some maybe problems with the toolpath, but otherwise,
With problems with super. Like
I'm not
that.
sure. Yeah, like the pads are like different sizes.
Yeah, I remember how they can do it.
Now you can do the drilling, I guess. Actually, yeah, now it started to print the infill. So if you want to see how does it look like, it's there. So you see, it just adds a fraction of the actual body. So you see, it's kind of zigzag. It creates a zigzag lines in between, and the rest of it is plain air. And it's just gonna cover it with something on the top.
because the outer material is transparent and the infill then you can have it filled. If there are two.
Ah, yeah, if there are two extruders, yeah. There was one experimental one which was with two nozzles, but yeah, I need to check.
Because the infill actually looks good in a way.
Yeah, so depends on the context, of course,
Yes.
if you want it to be visible or not. Yeah, and yeah, you can see here as well. So there's like an infill. So most of it it's just air, and then there are some infill parts just in order to be able to support.
One piece. So 20% means that 20% of the height you will choose to print, or just print like this way.
No, if you think of it about a volume, so let's say it draws around, so there's gonna be the shield, or the outer layer or the walls of the object, and then inside there's this plain air, you don't see what is inside, and then the percentage is how much of that inside is actually filled with plastic. Oops, like, it's really. I was quite shaking quite hard. I don't know what's going on there. So yeah, how much percentage-wise there's plastic? So 20% means that 20% of this inside, which is kind of air, it's going to be filled with plastic in some way. Yeah, that's that.
Also, the infill will be, it is decided by the slicer how it is structured in the volume, right? Like the rabbit that we saw in the YouTube video with the silk.
Yeah, so it depends on the slicer. Yeah, also you can specify some settings, so you can make it be triangular or rectangular or honeycomb or any other shape. So yeah, not any other shape, but the shape that is offered by the slicer, because it's
also the strength that you require for the walls. Also.
Yeah, you should take that into account. Yeah, this is the benefit of this technology. If you choose the settings right, and if you just need a basic prototype, then it can be very fast. But if you go with high detail, then it also might easily take up to 40 hours, like 24 to 48 hours. So with this one, so there have been prints that were printing for 4 hours and more. And yeah, usually with these very detailed prints, it's much more likely that the nozzle of the printer is going to jam. Have to be very careful with that.
And does the slicer tell you how much length you need of the roller?
Yeah, so it usually measures it in terms of grams. But then from that you can approximately tell how much. I very rarely do that, so usually so in this case it would be interesting to know, since there's a shortage of filament, so how much filament is going to use. But otherwise, yeah, it's more by intuition. Sorry?
I remember.
You didn't remove? It's 0.3.
Yeah, no, I mean, I remember it being longer. It didn't snap or anything.
Maybe it did. I need to check it under the microscope. Let me see. actually looks fine.
Fine. Okay.
It doesn't look like it would broken. We could also like check the ones that are fresh. So maybe we could get one fresh and then compare.
The other one seems longer. Right. There is another.
Can I see the labels? Yeah, 0.3, 0.3. 1, 2, 3, 1, 2, 3, 4. 0.8. Mm-hmm. Yeah, it is longer. Yeah. So this is fresh. So we actually broke it. Yeah.
Was it while? I don't know when that happened. I think now when I took it out, like it did touch the board a bit, but I don't think that was anything strong.
I don't know, but still it did mill. But yeah, I think this was the reason why.
You had the issue.
Yeah, with the layer thickness and everything.
But that was also the alignment. I don't know.
I think we can just throw this out. I don't know.
Yeah, usually they break.
Yeah, I think like so. This is also. It looks like the quality of those is not that good. I still need to get some, real carbide ones. It's gonna take time to order them, but apparently I think it's a good idea.
The same?
Yeah, I mean these are a bit different. So these are for drills. So these LS, you should use these LX for. So these are more milling bits. So for drilling, you could use these, but yeah, since they are different sizes of the holes, then this LS milling bit, it's gonna be better.
So for now, should I use that one, the L2S 0.8?
Yes.
Okay. And these are, is that the previous packaging? Or what are these?
These are drills.
No, this is just drills. Okay.
Almost done. Need to send one email as long as I remember.
Something confuses me about changing the bit.
Yeah. Okay, just a second. Okay.
We need it like to be more down when I put it, but otherwise I cannot really like insert it from between.
No, but first you put it up.
Up.
Yeah, you go up so you can insert the tool and.
Yeah, well, I mean I can insert it like.
No, you just go as much as you need in order to be able to insert it.
And then go down and then release it and then
Yeah,
insert it.
yeah, exactly.
For some reason I remember it was like a two-step, so I can just go up.
Yeah, exactly.
Which other formats can we give to slicer? Like you gave the format from Fusion 360,
No, it was more like a unified format. It's usually STL. So from
Yes.
Fusion 360, I did export an STL file.
yes.
So you can export an STL file from any other software like Blender or Rhino or
But it needs STM
yeah,
to be in slicer.
yeah. So I haven't checked it. I haven't got the need to use any other format really. Maybe it supports more, but STL is kind of the standard.
I would make a model then. Why does it need to make the outer line again?
That's for it's a good idea to do so because that's kind of the so that the printer makes sure that it starts actually extruding. So sometimes there's when it starts printing, then there's the filament hasn't reached the tip of the nozzle yet, and it's also sometimes used as a structural thing, meaning that it makes the first layer to stick to the build plate better. So, and our print is ready. Now it's cooling down the build plate, and when it's gonna be cool enough, then it's gonna bring it forward and kind of hand it to us as a cookie on a plate.
Alright, I'm setting in the drilling file.
Okay.
The same. I did the Z origin, and that's about it, right?
Yeah.
Speed.
Yeah, that's I think it's still. So this we're going to do on Friday.
How are you gonna do that? Alright, that's gonna take a while, I guess. Quite a lot of phone calls. That's just one layer. Or is it? No, it's just one, yeah.
Yeah, so if for the first time now, I thought it's a good idea to do it just from one side. So you will see that why I told you that it's best to do it from the two sides. So,
Yeah. You said you did it first half and then half. Well, you can still do that. But do you want to check how it looks like? Should I pause it?
No. But then you need to flip it over to other side. So it's just at this point it doesn't make much sense, you know. Still, it's gonna drilling. It's drilling through. It's just that some of the holes you will need to remove by hand.
And how the hell do sure these are like the bias?
Oh, that you have to tell from design.
Okay, just by design.
Yeah. Yeah. So now you can try to get it up from the build plate. Who's gonna try it? Instead of taking it. Yeah, but I would just try like yourself to remove it. So I think it's kind of fun. If it's stuck like this, so sometimes if you can use force, that is just enough, but you can use tools like these. Oh, you managed, yeah. So
Yeah.
cool. Yeah. Looks like it worked out nicely, and so what I also did these elevated parts. So here on the bottom side there are the supports. In this case, they are kind of hard, but usually they should be quite easy to remove. In this case, it's not so easy. Maybe, yeah. Yeah, this is not good. So this is why also the limitation of FDM technology. So if you have a single nozzle, then usually you will need to use supports, and you might end up with ugly things like these. So at this point you would say, oh, okay, I need to change my design. So it actually touches the build plate in the first place. I hate this. It looks so ugly. Yeah. So.
I understand why you trying to do that.
Yeah, because it was it's supposed to be like on this side, you see.
But it's impossible, isn't it?
No, it's possible. I mean, if you edit the settings of the supports, you could generate supports that are nice eventually. But these were kind of a bit not nice. Well, yeah, so I created this groove. So, for example, you would make something like this. It would spin around and sit on an edge. Then maybe it would make sense.
Yeah.
It's more like a train or a train. Yeah, you would build a toy train than this one. So yeah, but yeah, feel free to experiment from now on. I think I'm just gonna put this in the camera like so.
Yeah.
That it's recorded. This is the result with this ugly, with the ugly side of it, and this is the nice side of it. So this is why you don't want supports. Okay, yeah. Thanks for watching.
But do you think I can come tomorrow and we actually do those things?
Sure. Yeah. Yeah. Feel free. That's you know. There are not too many people. If it would be full, like 15 people, 20 people, then it would be an issue. But in this case, it's
But do I
you know, university is about teaching new things,